Hello, everyone. My name is Qing Tang, a PhD student from Penn State University. And the topic I'd like to, I think is the development and the testing of autonomous maintenance technology for work zone. And here is my presentation outline. First is the background of our research, and then one CAV technology for work zone, ATMA, autonomous truck-mounted attenuate system will be introduced. And next is the system testing and the performance evaluation. And last section is the driver operation guidelines. Maintenance in work zone is important. U.S. Department of Transportation spent $24 billion to preserve a national highway system in 2020, but it could be dangerous. And many crashes involved DOT workers, and in 2019, a crash happened every 4.6 minutes and 74 crash-related injuries daily. 18 crash-related fatalities weekly. So how to protect the lives of DOT workers? As the rapid development of CAV technologies, many state Department of Transportation tend to use the autonomous truck-mounted attenuate system to reduce the fatalities of workers in work zones. One specific technology named autonomous truck-mounted attenuate system is being tested and deployed in several states. And the system includes one leader truck and one follower truck, which installed and equipped with truck-mounted attenuate. And this system enables the follower truck to drive autonomously and thus remove the drivers. During the ATMA performs a maintenance operation, the velocity, heading, and position information will be connected by a navigation computer and then transmits that information in packets of data called crops. And then those data will be transmitted to the unmanned follower truck over the vehicle-to-vehicle communication link. Those transmitted prompts enable the follower truck to follow precise position, speed, and the direction of the leader truck. In order to test the system performance, that is to see whether the system elements meet the predefined accuracy and functional requirements. So there are a total 31 test cases designed to test, and including 23 quantifiable test cases, for example, communication loss test, fallen distance and accuracy test, obstacle detection test, and emergency situation test, and also include 8 yes or no tests. That is the visual inspection, data logging, turning signals, and the functionality on the user interface. And our expected results are the system can function as expected and pass the predefined criteria. For example, those natural cross-track arrows within positive and negative 6 inches, and then the longitudinal cross-track arrows within the positive and negative 15 feet. And each test was repeated for 3 times for statistical accuracy. And the test is operated for a minimum of 32 consecutive hours. Here is the data we collected from the field testing. And the first table is the data from the leader truck, including the time and the position, location, including the latitude, the longitude, and the altitude, and also including the heading distance and the velocity. And then the second table is the data of the unmanned follower truck. Apart from the above information, it also includes the desired heading way and the actual headway and the gap distance and the desired gap distance and the velocity and etc. For those quantifiable tasks, we needed to further analyze the cross-track errors to determine whether the tasks have passed or not. First, statistical characteristics of the cross-track errors, including the mean value, standard deviation, and quantiles to illustrate the system's overall performance and compared with predefined criteria. And after that, we also expect that the system would function stably each time, so its function consistency needs to be tested also. So based on the data connected for each test case, the probability distribution of the cross-track errors frequency was analyzed to determine the probability that the cross-track error fell within a certain range. Then we did a hypothesis test to prove the system could function consistently. So we choose the fragment test and we also choose the confidence level alpha equals to 0.05. Here we present some examples of the test results. And two test results of the communication loss test are shown here. One is the radio frequency loss test, and the other is the single vehicle-to-vehicle radio loss test. And these two figures are showing the frequency distribution histogram of the cross-track error, and the x-axis is the cross-track error in inches, and the y-axis is the frequency. So as we can see, for the three tests, repeated tests, we can find that more than 96.5% cross-track errors are within positive and negative 6 inches, and the p-value is greater than 0.05. So which means that the results are consistent. And for the second test, we can also find that all the cross-track error are within the positive 6 and negative 6 inches. And the p-value is also greater than 0.05. Also, here are 4 examples of following distance and accuracy tests. We can also derive that the test was passed and performed consistently. Other test results can be directly observed. For example, the obstacle detection tests, we can say that the follower truck detected the barrier and executed an A stop, and also the object detected was displayed in the user interface in the leader truck, and the driver can also see that. And for the other emergency situation tests, it can be observed that the follower truck could catch up to the set gap distance and stop or disengaged from the system, and the distance errors were within our predefined criteria. So for field testing and the results analyzing, we can conclude that the ATMA system was able to function as expected, and its performance was acceptable comparing with our predefined criteria. And through the hypothesis testing, we can also find that the system was able to function consistently when the testing was repeated. Before the ATMA system is applied in work zones, the operation guidelines for drivers are needed to be considered at first, because the unique leader-follower system design impose more requirements on our leader truck drivers to ensure a safe driving and a smooth system operation. So especially in three critical decision-making locations, that is the carpooling, lane changing, and the intersection. We need to define how much the carpooling distance is safe and how many gap distance needed to make a lane change, and also how many clearance time the system needed to cross this intersection or make a left turn at the intersection. So that next, the model will be developed to determine the minimum driving requirements for the leader driver. In carpooling model, the minimum carpooling distance for leader truck is the distance traveled in his or her reaction time plus the braking distance to make safety. And since the follower truck is unmanned, so there is no reaction time, but we need to consider a system errors optional. So, and we also need to consider the roll ahead distance. In the work zone, a truck mounted attenuate equipped vehicle should be positioned at a sufficient distance in advance of the workers or equipped being protected. And this is the figure shows the minimum carpooling distance of a leader truck, and the x-axis is the operating speed of the system, ranging from 5 miles per hour to 15 miles per hour, and the y-axis is the distance in feet. So we can find that the minimum carpooling distance for the leader truck is 75 feet. And for the follower truck, the minimum carpooling distance depends on the speed limits, which determine the roll ahead distance. So it ranges from the 100 feet to 172 feet. For the lane changing gap requirement, this figure shows the critical lane changing gap of ATMA vehicles. In this figure, the leader truck and the follower truck on the lane 2, and they would like to change lane to the lane 1. So for the leader truck, so the total gap distance includes 3 components. The first one is the leader gap distance for the leader truck, and the second is the gap distance required for the follower truck to switch lanes. And the 3 components is the lag gap distance for the lagging general vehicle on the target lane. So those 3 components also can correspond to 3 criteria time headway. So the results show that if free flow speed is set to be 70 miles per hour, and the preset gap distance is set to be 100 feet, and then the critical time headway for lane changing is 25 seconds. And if the gap distance is set to be 200 feet and the time headway required is 27 seconds for make a lane changing. At the intersection, we need to decide the minimum clearance time for both trucks cross, go straight at the intersection or make a left turn. So in this figure, a specific 4-lane, 2-way highway intersection profile is illustrated. And the leader vehicle needed to, the leader driver in the leader truck will need to decide whether the remaining green time is enough for both truck make a left turn or cross the intersection. So the results show that the time required for crossing this intersection or making a left turn are almost equal, because the lane wise and the intersection lengths are almost the same. So when the gap distance is set to be 100 feet, and the clearance time required is range from 10 seconds to 31 seconds. And as the gap distance is increased, and the time will also increase corresponding. And then after that, combining with the connected autonomous vehicle technology, we can apply the guidelines to the work zone. Because the ATMA vehicles will be installed in many sensors such as radar, LiDAR, ultrasonic cameras. They can detect the obstacles and the gap distance. And also applying the vehicle to infrastructure communication, those information from the traffic signal controller will be provided to the driver, and they can decide the clearance time at the intersection is enough or not. So that's it. Thank you. Is there any question?